Find the inflection points and regions of concavity for the function f of x equal to absolute value of x squared minus 4x minus 12. So, to answer my question, we need to get our hands on the second derivative. But to do that, we're going to have to get around the absolute value signs. So first, definition of absolute value. If I take the absolute value of y, what do? If y is bigger than or equal to 0, we do nothing. We just return y. If y is less than 0, there's a minus sign out in front. We get rid of the minus sign by multiplying by minus 1. So absolute value of y, if y is negative, is just minus y. Now, wherever I have a y, we're going to place the inside of our function. So that's going to be y equal to x squared minus 4x minus 12. So that's going to be here. So what we're going to have to do is, we're going to have to solve for the regions where x squared minus 4x minus 12 is greater than or less than 0. The way I'll do that, we'll factor, we'll find the zeros, and then we'll check one point on each region. Okay, our function's a polynomial, so it's continuous. So once I know where the zeros are, I can get the sign of any region by checking one point. So we do that. Our zeros are going to be at x equal to minus 2 and x equal to 6. So I'm going to check a point in each region. What can we do? Well, if I take 0, we're going to have a negative number. So the region in the middle will be all negative numbers. So in that region, we're going to multiply by a minus 1 for our inside function. Then we can use, say, 10 for the region bigger than 6. That's going to give me 12 times 4, which is positive. So we're positive on this region. If I use minus 10, I'll get minus 8 times minus 16, which is definitely positive. So we'll be positive on this region out here. So if I rewrite my function, what do I have? I'm going to have x squared minus 4x minus 12 when x is bigger than 6 or x less than minus 2. And then between minus 2 and 6, we're going to have 12 plus 4x minus x squared. So that's my function. Now I can take the derivative of each piece. So what happens then? For bigger than 6, less than minus 2, our derivative is 2x minus 4. Note, we could try to find the critical point there, but that would happen at 2. The point x equals 2 is not in that region. Take the derivative of the second piece. We're going to have minus 2x plus 4. Here, if I solve for the 0, we're going to have critical point at x equal to 2. So we can mark that off on our graph. Now, you'll also note we're going to have two other critical points where we're at our breakpoints. So that's where the two functions here, where the regions meet up. So for instance, at minus 2, let's check the derivative coming in from each side. If I put minus 2 into the first part, we're going to get minus 8. I put minus 2 into the other part, we're going to get 8. They don't agree, so the derivative has a does not exist at minus 2. And we see on the graph, that's going to result in a corner. Okay, same idea when x equals 6. So we'll have 3 marks for checking increasing and decreasing. Since that's not the problem we're looking for, I'll leave it to you to figure out how to fill in the top boxes. Okay, that's f prime. Now we can do f double prime, second derivative. What happens? Okay, well, on our middle region, we're going to get a minus 2. And then on the outside regions, we're going to get a 2. So, again, note what happens here. So here, we're only going to have points where the second derivative is undefined, where our two regions meet up. So I'll have lines drawn in at minus 2 and 6. That's where second derivative is undefined. There are no points where the second derivative is equal to 0, so we don't have to worry about that. And so now I just have to check one point in each region, but no need to check any points. We know what the value of the function is if I take any point in the regions. So if I'm in the middle region, we're going to have a minus 2, which means we're concave down. The graph bears that out. And then if I'm on the outside regions, I have 2, which means I'm concave up, and the graph bears that out also. Now, to remind yourself of how we're getting the graph, just remember I have a parabola. That's what x squared minus 4x minus 12 looks like. And then anything that's under the x-axis just gets flipped up. Final part, inflection points. So technically, there's no inflection points here. To have an inflection point, we would need to have a change in concavity. So we do have changes in concavity at our -2 and our 6, but we also want in our definition that the first derivative is defined there. So we want that a tangent line exists. Since that's not the case here, we have no inflection points.